Hey, welcome back to ClearSpot. What if I told you that 97% of commercial solar installations have major performance issues that could be costing you thousands of dollars every single year? And what if I told you that there's a hidden enemy called potential-induced degradation that can silently steal up to 50% of your solar panel's power output without you even knowing it's happening? Today we're diving deep into the world of solar performance troubleshooting. Not the basic stuff you'll find in homeowner manuals, but the advanced techniques that monitoring experts use to diagnose and fix problems that most people never even know exist. Over the next 25 minutes, I'm going to take you through a comprehensive troubleshooting journey that covers everything from the subtle signs of potential-induced degradation that can reduce panel efficiency by up to 30% to the advanced IoT-based fault detection systems that achieve 96.32% accuracy in identifying problems before they become expensive failures. We'll explore real-world case studies where proper troubleshooting increased energy yield by 27% and reveal the cutting-edge AI techniques that are revolutionizing how we detect and solve solar performance issues. This isn't just about fixing obvious problems. This is about becoming a solar performance detective who can identify issues that are invisible to the naked eye, but are quietly draining your system's efficiency and your wallet. Before we can troubleshoot any solar performance issue, we need to understand what normal performance looks like for your specific system. This is where most people make their first critical mistake. They assume that any electricity production means their system is working fine. Solar panels will rarely generate their nameplate wattage because they are tested under ideal laboratory conditions, which are not achieved in rooftop installations. The key to effective troubleshooting is understanding that you can have two homes with 360-watt solar panels of the same brand, and their electricity output can vary widely due to factors like local sunshine, roof orientation, and ambient temperature. This means your troubleshooting approach must be tailored to your specific installation conditions. Professional solar monitoring experts track several key parameters that most homeowners never consider. IoT-enabled sensors offer the capability to collect real-time data on key parameters, such as solar irradiance temperature, voltage, and current, allowing for comprehensive monitoring of system performance and environmental conditions. But it's not just about collecting data, it's about understanding what that data tells you about your system's health. Voltage and current measurements are your first line of defense against performance issues. The photovoltaic array open voltage circuit should be measured to confirm that it is within normal limits. When these readings deviate from expected values, they often indicate specific types of problems that require different troubleshooting approaches. One of the most sophisticated aspects of professional solar troubleshooting is, honestly, just understanding how environmental factors affect performance. The system uses voltage, current, and light-dependent resistor sensors to monitor key panel parameters in real time. This comprehensive monitoring approach, well, it really lets experts distinguish between normal environmental variations and actual system faults. Temperature monitoring is especially crucial because, solar panels sometimes struggle to convert sunlight into usable energy efficiently due to a bunch of factors, including improper installation, shading from objects, dirt accumulation. Understanding these relationships helps you figure out whether performance issues are environmental or equipment-related. Professional solar troubleshooting, it actually follows a systematic approach that starts with the big picture and then narrows down to specific components. First, check the output of the entire system at the metering system or inverter. Before you even begin troubleshooting, check and record the inverter's input voltage and current level from the array. This gives you a baseline understanding of whether you're dealing with a system-wide issue or, a localized problem. The methodology involves two primary scenarios. The entire PV system, or a portion of it, is down or not producing power, which may be related to a problem with the inverter. Or, the PV system output is less than expected, which may be related to a problem with one of the arrays or modules. Each scenario, of course, requires a different diagnostic approach and troubleshooting strategy. Modern troubleshooting has really been revolutionized by artificial intelligence and IoT technologies. AI algorithms, including machine learning and deep learning techniques, enable automated fault detection, predictive maintenance, and anomaly identification based on collected data. These systems can identify problems that, honestly, would be impossible for human operators to detect through traditional methods. The experimental results indicate that ALM achieves a classification accuracy of 96.32%. which is higher than SVM and other optimization control techniques. This level of accuracy in fault detection means that AI-powered systems can identify problems before they become visible through traditional monitoring methods, potentially saving thousands of dollars in lost energy production. One of the most powerful troubleshooting tools available today is thermal imaging analysis. This study presents a deep learning-based approach to identify internal faults in solar panels, using sensor data and thermal imagery obtained from drones equipped with infrared cameras. This technology can detect problems that are completely invisible to visual inspection. Drone-based inspections, powered by AI for image processing and analysis, are making monitoring of large solar installations faster and safer, automatically identifying issues like microcracks, dirt accumulation, or structural damage. What used to require weeks of manual inspection can now be accomplished in a single day with far greater accuracy and detail. Let's start with one of the most insidious problems in solar systems: potential induced degradation, or PID. PID arises from stray electrical currents within the solar panel. These currents gradually disrupt the delicate internal structure of solar cells, reducing their ability to efficiently convert sunlight into electricity. The terrifying aspect of PID is that it can lead to significant power losses over time, up to 30% in severe cases. PID is fundamentally caused by the movement of charged particles or ions within the solar cell under high voltage stress. These ions interfere with the cell's photovoltaic function, compromising long-term performance. The challenge with PID is that it develops slowly and can go undetected for years while silently stealing your system's performance. Detecting PID requires specialized techniques. Use an insulation resistance tester to check the panel and ground resistance. Low insulation resistance could be a sign of PID. Professional troubleshooting also involves inspecting the grounding of your solar system to ensure all components are properly grounded according to manufacturer specifications to prevent exacerbating PID. Inverter problems are among the most common issues in solar systems, and proper troubleshooting requires understanding the specific fault codes and their meanings. Many inverters display error messages like grid fault, overvoltage, or isolation fault. These indicate common inverter problems caused by grid fluctuations, wiring issues, or internal component faults. Modern inverters, like those from Solus and SolarEdge, feature maximum power point tracking, or MPPT. Ensure this function is enabled and configured properly. When troubleshooting inverter issues, look up the error message in your inverter's manual or on the manufacturer's website and perform a system reset using the power cycle method. Advanced inverter troubleshooting involves checking multiple parameters. If the photovoltaic reading is close to the open circuit reading of the panels, and then the battery reading is low, the controller is possibly not charging the batteries itself and may be a sign of battery damage. This type of diagnostic thinking separates professional troubleshooting from basic homeowner maintenance. Hotspots represent one of the most dangerous performance issues in solar systems. Hotspots are one of the most common solar panel problems. When disruptions occur in a panel's energy production pathways, it becomes overloaded and radiates excessive heat. These hotspots can cause permanent damage and create fire hazards if left unaddressed. Partial shading and accumulation of dirt often cause reduced performance or permanent damage. The key to professional hotspot troubleshooting is understanding that hotspots are better prevented than repaired. This means implementing monitoring systems that can detect the early signs of hotspot formation before they become dangerous. Advanced hotspot detection uses thermal imaging to identify temperature variations across panels. AI algorithms identify and localize hotspots on solar panels, which indicate areas of excessive heat that can reduce efficiency and potentially lead to damage if left unchecked. This technology allows for precise identification of problem areas that would be impossible to detect through visual inspection alone. Shading is one of the most complex troubleshooting challenges because its effects can be subtle and change throughout the day and seasons. Shading on solar panels can greatly lower their power output. Trees, buildings, or even chimneys can cause shadows that reduce efficiency. But professional troubleshooting goes far beyond simply looking for obvious shadows. Even partial shading can significantly decrease energy output. The challenge is that shading from nearby trees, buildings, or other obstructions can significantly reduce solar panel efficiency. Professional troubleshooting involves analyzing shading patterns throughout the day and across seasons to identify both current and potential future shading issues. Advanced shading analysis uses specialized software and monitoring data to model shading impacts. Trim or remove obstructions causing shading. Alternatively, consider installing microinverters or power optimizers to mitigate the impact of shading on individual panels. This approach requires understanding how different mitigation strategies affect overall system performance and economics. Dirt and contamination represent ongoing challenges that require systematic troubleshooting approaches. Dust and dirt can accumulate on the surface of solar panels, partially blocking sunlight and decreasing their energy output. But professional troubleshooting recognizes that different types of contamination require different solutions. Pollen can have the same effect as dirt and dust during the flowering season of plants. This seasonal variation means that troubleshooting must account for time-of-year factors and local environmental conditions. Regular cleaning and maintenance are essential to ensure optimal functionality. Advanced contamination analysis involves understanding the specific types of soiling affecting your installation. Use AI to detect dirt, dust, and other debris accumulation on solar panels, allowing for timely cleaning to ensure maximum energy absorption and efficiency. This technology can distinguish between different types of contamination and recommend appropriate cleaning strategies. Physical damage assessment requires understanding both visible and invisible forms of panel degradation. So, you'll want to physically inspect your solar panels for any visible damage, such as cracks or dirt accumulation. But professional troubleshooting goes much deeper, using advanced techniques to identify damage that isn't visible to the naked eye. It's important to identify microcracks or fractures in the solar cells that are not visible to the naked eye, because this helps prevent long-term damage and efficiency loss. These microcracks can significantly impact performance while being completely invisible during standard visual inspections. Advanced physical assessment techniques also include understanding degradation patterns. Even the most efficient solar panels become less productive over time, but this happens at a very slow rate. Typically, the annual productivity loss is less than 0.5%. When degradation exceeds these normal rates, it indicates specific problems that require targeted troubleshooting approaches. Electrical troubleshooting in solar systems requires understanding both DC and AC side issues. So, you'll need to trace out the individual branch wiring backward from the concentrator. Check the entire system visually for any obvious damage or accidental disconnections. This systematic approach ensures that no potential connection issues are overlooked. Professional electrical troubleshooting involves checking multiple connection points. Once you find the failed module or array, check all wires, switches, fuses, and circuit breakers. Replace blown fuses, and don't forget to reset the breakers and switches. The key here is understanding how different types of electrical faults manifest in system performance. Advanced electrical diagnostics use specialized testing equipment. Check for broken wires and loose or dirty connections, and replace or clean as needed. Be on the lookout for loose connections between the modules. These connections may have worked loose and cause lack of contact, leading to performance issues that can be difficult to diagnose without proper testing procedures. Grounding system integrity is crucial for both performance and safety. You'll want to inspect the grounding of your solar system. Make sure all components are properly grounded according to manufacturer specifications to prevent exacerbating PID. Improper grounding can lead to multiple performance and safety issues. Professional grounding troubleshooting involves understanding the relationship between grounding and system performance. The battery connection should be checked because the inverter could possibly be damaged and needs to be replaced. This type of systematic checking ensures that grounding issues don't cause expensive component failures. Advanced grounding analysis includes understanding how grounding affects different types of faults. Spot signs of corrosion on solar panels and mounting structures, ensuring timely intervention to prevent structural failures and maintain system integrity. Corrosion in grounding systems can create both performance and safety hazards. Load balancing troubleshooting requires understanding how different loads affect system performance. The fuses could possibly be damaged or defective if this is the case. You'll want to check the fuses to ensure they are not frayed or damaged. But professional troubleshooting goes beyond simple fuse checking to understand load distribution across the system. Advanced load balancing analysis involves understanding system capacity and demand patterns. A shutdown might have occurred due to an overload in the system and might have exceeded the solar inverter's surge capacity. This type of analysis requires understanding both the electrical characteristics of your system and the load patterns of your facility. Professional load optimization includes understanding how different system configurations affect performance. The rating of the photovoltaic array may have exceeded the rating, so another controller in parallel should be added if needed, or replace it with a controller that will be able to accommodate the rating. This approach ensures that system components are properly matched and optimized for maximum performance. Modern solar troubleshooting relies heavily on comprehensive monitoring systems that provide real-time insights into system performance. The system utilizes voltage, current, and light-dependent resistor or LDR sensors to monitor key panel parameters in real time. This data is transmitted to a cloud platform for storage and analysis. This level of monitoring enables proactive troubleshooting before problems become expensive failures. Advanced monitoring systems provide multiple layers of analysis. Users can access this data through a mobile app, enabling remote tracking of energy generation, promoting proactive maintenance, enhancing efficiency, and contributing to a sustainable energy future. This remote access capability allows for continuous monitoring and rapid response to performance issues. Professional monitoring implementation involves understanding data interpretation. By automating fault detection, the system ensures early identification of issues, minimizing downtime and optimizing energy output. The key is not just collecting data, but understanding what that data tells you about system health and performance trends. The future of solar troubleshooting lies in predictive maintenance powered by artificial intelligence. AI algorithms, including machine learning and deep learning techniques, enable automated fault detection, predictive maintenance, and anomaly identification based on collected data. These systems can predict problems before they occur, allowing for proactive maintenance scheduling. Advanced AI systems provide unprecedented accuracy in fault detection. The experimental results indicate that ELM achieves a classification accuracy of 96.32%, which is higher than SVM and other optimization control techniques. This level of accuracy means that AI systems can identify subtle performance issues that would be impossible for human operators to detect. Professional AI implementation involves understanding the different types of machine learning approaches. By leveraging the synergy between IoT and AI, solar panel monitoring systems can achieve higher levels of efficiency, reliability, and autonomy, ultimately leading to improved energy production, reduced maintenance costs, and enhanced system resilience. This comprehensive approach transforms troubleshooting from reactive problem-solving to proactive system optimization. Advanced troubleshooting increasingly involves integration with smart grid technologies. IoT, facilitates real-time data collection, remote monitoring, and automated control, ensuring optimal system performance. This integration allows for troubleshooting that considers not just individual system performance, but how that system interacts with the broader electrical grid. Smart grid integration provides new troubleshooting capabilities. AI techniques enhance operational efficiency by detecting faults early, predicting maintenance needs, and improving energy forecasting. This holistic approach to troubleshooting considers system performance in the context of grid conditions and demand patterns. Professional smart grid troubleshooting involves understanding bidirectional communication systems. Meanwhile, IoT facilitates real-time data collection, remote monitoring, and automated control, ensuring optimal system performance. This two-way communication enables troubleshooting approaches that can optimize system performance based on real-time grid conditions and demand forecasts. Professional solar troubleshooting requires specialized equipment that goes far beyond basic multimeters. Use an insulation resistance tester to check the panel and ground resistance. Low insulation resistance could be a sign of PID. This type of specialized testing equipment allows for diagnosis of problems that would be impossible to detect with basic tools. Advanced diagnostic equipment includes thermal imaging cameras for hotspot detection. This study presents a deep learning-based approach to identify internal faults in solar panels, using sensor data and thermal imagery obtained from drones equipped with infrared cameras. This technology allows for comprehensive system analysis that can identify problems across large installations quickly and accurately. Professional troubleshooting also involves understanding when to use different types of diagnostic approaches. Traditional methods of fault detection often involve manual inspections, which are labor-intensive, time-consuming, and less feasible for large or remote installations. Modern troubleshooting combines traditional techniques with advanced technology to provide comprehensive system analysis. Understanding the limits of DIY troubleshooting is crucial for system safety and performance. For more complex issues, Greenlancer can connect you with experienced professionals to help repair your solar inverter and restore optimal system performance. Professional troubleshooting becomes essential when dealing with high-voltage systems, complex electrical faults, or safety-critical issues. Professional help is particularly important for advanced diagnostic techniques. The proposed system analyzes historical voltage and current values to predict faults and assess their impact on energy generation. This type of analysis requires specialized knowledge and equipment that goes beyond typical homeowner capabilities. The future of solar troubleshooting is being shaped by emerging technologies and methodologies. In future developments, the model could be extended to identify visible panel defects from standard RGB images, making it a versatile solution for real-time PV system monitoring. This evolution toward more sophisticated automated troubleshooting systems will continue to improve system reliability and performance. Advanced troubleshooting will increasingly rely on integrated systems that combine multiple diagnostic approaches. By harnessing IoT-enabled sensors for real-time data acquisition and AI algorithms for tasks such as fault detection, predictive maintenance, and performance enhancement, solar panel monitoring systems stand to achieve heightened precision, scalability, and autonomy. This comprehensive approach represents the future of professional solar system troubleshooting. We've covered a comprehensive journey through advanced solar troubleshooting techniques that separate professional monitoring experts from basic system owners. From understanding how PID can silently steal up to 30% of your system's performance to implementing AI-powered diagnostic systems that achieve 96.32% accuracy in fault detection, these techniques represent the cutting edge of solar system optimization. The key to becoming proficient in solar troubleshooting is understanding that it's not just about fixing obvious problems. It's about implementing systematic monitoring and diagnostic approaches that can identify and prevent issues before they become expensive failures. By automating fault detection, the system ensures early identification of issues, minimizing downtime, and optimizing energy output. Professional solar troubleshooting is evolving from reactive problem-solving to proactive system optimization. With the right knowledge, tools, and techniques, you can transform your solar system from a passive energy generator into an intelligent self-monitoring power plant that operates at peak efficiency for decades. The future of solar energy isn't just about better panels. It's about smarter troubleshooting and monitoring that ensures every ray of sunlight is converted into maximum value for your investment. Like, share, and subscribe for more solar insights. ClearSpot, smart device, smarter decisions.